All right, now let's do some E&M. So, this is Form J, the one that was given to the most students. But I know personally, my students, about half got J, and then uh, half got sort of M and K combined in there. So if you think you got a harder form, it's very possible your questions were harder than this, but don't worry, the individual cut scores are exam dependent. So you're only judged on a scale of people who took your specific exam when they do the setting. So there's different cut scores depending on what letter you had. So this is J. I thought this was a very typical form. I know my students felt really good about it. But sort of the only weird question on here, I think, that had a slight twist to it was probably this question one. So question one has us looking at this cylindrical capacitor setup, where there's an inner and outer conducting cylinder, so you know all the charges on the surface, and it gives the surface charge densities. And to make this a capacitor, the sigmas aren't equal because the areas aren't, but the total charge is. So we know that this is an equal and opposite charge situation. So we're given each radius, we're given each sigma, and the length of the cylinder. Part A says first, using Gauss's law, so we better use Gauss's law, derive an expression for the magnitude E of the electric field as a function of the distance from the center in the in-between region. So we're interested in the field between the two capacitor plates, even though they're not plates. So we're interested in the field somewhere in that central cavity. So due to the symmetry of this problem, we know that we are going to be drawing some sort of a cylindrical Gaussian surface, because if I draw a cylinder that's concentric with the other one, it's going to pierce, the electric field will pierce the cylinder at every point, making our flux integral easy to evaluate. So it says starting from Gauss's law, so I better write Gauss's law. So I'm going to start by writing Gauss's law. Which just tells us that the electric flux, integral v dot dA, is equal to Q enclosed over epsilon naught. It is never the left side of Gauss's law that is hard. The left side of Gauss's law, even though it has the integral on it, always simplifies because we pick a clever surface. So we picked a cylinder of radius little r because that's the thing that varies. So we don't want the field at a specific location, we want it for any r in that in-between region. So we use the area of a cylinder, which is 2 pi r, for the ring of the cylinder, and then L for the distance it extends. And then for Q enclosed, this is the one part of this problem I thought would be a bit weird. So for the Q enclosed, we're not given Q, but we're given sigma. So this is truly a what the sigma moments, because you had to figure out how to translate the charge density to the enclosed charge, but we can see that the enclosed charge is everything that's enclosed by cylinder 1. So cylinder 1 has a charge density on its surface, sigma 1, and then we got to find its area to figure out the total charge. And we'll just continue this. So it is once again a cylinder, but this time we're going to use a radius of big R1 times the length, because the cylinder that we're enclosing charge on has a fixed radius. And now we just do some simplifying, and this actually works out quite nice. So E times 2 pi RL is equal to 2 pi R1 sigma 1 L over epsilon naught. And then virtually everything cancels. So my 2 pi cancels. I don't know why I changed the L to lowercase there. And we get a very simple result, actually, that says E is just equal to sigma R1, sigma 1 R1 over epsilon naught R. And notice that this is consistent with what we found from E for a wire, because E from a wire, or a cylinder, falls off not like 1 over R squared, but 1 over R. Now that we have electric field, we can calculate the potential difference between the inner and outer sphere. Inner and outer shell of the cylinder. So we are just going to find the absolute value of the potential difference, and we're given that potential is just going to be what we get by adding up all of the downhill contributions of the electric field. Because if the electric field is the slope of potential, if we add up all of those slopes, we get our height change. And we want the height change between R1 and R2. So we're just going to integrate our E field expression between those two distances. So we're just going to integrate from the inner cylinder to the outer cylinder, and we have an expression for E. It's just sigma 1 R1 over epsilon naught times the quantity 1 over R with respect to R. And I factored that out because that's the only variable. So we just get sigma 1 R1 over epsilon naught times the integral from R1 to R2 of dr over R. And that's just a natural log situation. So we just get sigma 1 R1 over epsilon naught natural log of R evaluated from R1 to R2. And you could write this as subtracted logs. So you could write this as sigma 1 R1 over epsilon naught times ln R2 minus ln R1. Or we could compactly write this using the subtraction rule for logarithms as ln of the quantity R2 over R1. Of course, whatever form you wrote it in, if it's equivalent to this, it does not matter. So I repeat, if you wrote ln R2 minus ln R1 and left it like that, you will not lose any points. We just want a consistent expression. I think this one looks neater, so I put that there. On the axis shown, sketch a graph of E as a function of 0 to outside the shell. So first of all, we know that these are two conductors. So anything inside a conducting shell would be 0, but they actually don't have thickness. So beginning, we see that if I am in the center of this R1 shell here, I'm not enclosing any charge. So I'm enclosing absolutely 0 charge, and thus have 0 electric field, until I reach the first conductor. And then I instantly collect all of the charge on that conductor because it's all on its surface, and that field will decay in the cavity. I might make it more pronounced that it's a curve to the second conductor, but then as soon as you go on the second conductor, you collect all of its charge, which is equal and opposite. So outside the system, we have 0 charge as well. And not that we had to write the functional dependency here, but I'm just making this clear that I was intending to make a 1 over R graph here. And technically, this would be approaching infinity on this side, but close enough. So maybe I might make that even a bit better here. Something like this. In the real world, these conductors do have thickness, so it would be a bit different looking graph, but that's what we're going for here. And now for our B derivation, this is more related to A than I would have thought we'd get. Usually they make it a noticeably different derivation for B. So I feel like there were some things you had to get right on A to have success here. But alas, here we are. Now we're filling the conductor region between them with a dielectric. So we should be thinking about capacitance. And unfortunately, this is not a parallel plate capacitor, so we can't use C is epsilon naught A over D with a kappa there. We have to use the definition. So the definition of capacitance, which is what we're trying to find of this system, capacitance is defined as the magnitude of the charge on either surface divided by the absolute value of the potential difference between the two surfaces. And we can actually find this because we can figure out what Q is. We already did actually. And we can find what delta V is. So what I'm going to do first is I'm not going to incorporate the dielectric at first because it's really easy to translate if we know what it does in a vacuum first. So C, without a dielectric, is just going to be the charge on one cylinder, which we said was sigma 1 times 2 pi R1L. And then the magnitude of the potential difference is going to be whatever we did in the second part of that derivation. So I actually have to check back and see what it is. Sigma 1 R1 over epsilon naught ln of R2 over R1. And now actually a whole bunch of stuff does cancel. So the sigma 1 R1 does cancel from both the top and the bottom. So we're going to be left with the capacitance in a vacuum is 2 pi epsilon naught L divided by the natural log of R2 over R1. But that's not quite what we wanted, right? We put a dielectric in here, but that's a really easy translation to make because we know that by definition of capacitance, what we say that kappa does is kappa is the factor that it increases your capacitance by via, instead if it was, as opposed to being in a vacuum. So all we have to do is put a kappa in front because technically kappa is changing epsilon naught to kappa epsilon naught. So 2 pi kappa epsilon naught L divided by ln of R2 over R1. And notice this looks really similar to the cylindrical capacitance formula we derived in class / the freaking packet. I know we did this at some point. So there's question 1. This is probably the least standard of the 4, actually, and there's a lot of relevant things here. So let's actually go for a point breakdown now. So part A, this is going to be where I have to do some estimating because we know how the points are distributed, but not how they go through all the subparts. So we know that the deriving point on A is worth 5. And I would think the Gauss's law part is worth 3 of the 5. So first point, you would get a point for a multi-step derivation that uses Gauss's law. Next, you would get a point most likely for substituting into the left side of Gauss's law with a Gaussian cylinder of radius r. Usually you get a point for using the correct Gaussian surface, and then you get a point for a correct answer. Then for 2, we'll have 2 points dedicated here based on subtraction. You get 1 point for a valid expression for potential difference that you're deriving with, and then you get another point for a consistent integration of your electric field. So if your electric field is wrong, as long as you integrated it, you should be getting full credit here. Then the diagram is always worth 2 points on A. So you probably get 1 point for a decreasing electric field in the cavity region, and then you get a point for 0 field inside / outside the capacitor in between region. So the 0 regions is a point, and the not 0 region is a point. Now for B, this is a 3-pointer. You get a point for a valid expression of potential difference, capacitance. You probably get a point for a consistent substitution for Q and delta V using your previous expression. And then you likely get a 3rd point for an answer that shows kappa being multiplied. Again, not totally sure that's how it will be distributed, but I really think it's that way. I imagine you get a point for understanding that kappa is increasing the vacuum capacitance. So maybe, no, I feel like we get no points if we use the parallel plate capacitor formula. You might be able to sneak one out in there if it's showing the kappa, but again, that's a classic mistake I saw, because this is tricky, this definition of capacitance. A lot of people went to the parallel plate, but unfortunately this is not plates. Regardless, I still thought there were a lot of gettable points here, even if you did not get the clean sweep. All right, now we have the induction question. So anyone who did my free response of my practice exam, this should look very familiar. So it looks like almost identical to part B of one of my questions I wrote, where it was setting up talking about power of a rotating loop, just like this. I actually didn't give you the area. So it's actually easier than the one I wrote. A rotating circular conducting loop of area A, resistance R, is in an external magnetic field. It's rotating at angular velocity omega. And we don't even have to do any guessing here. It tells us specifically that flux as a function of time through the loop is BA cosine omega t. So for our TBR, we start with a representation that's not a graph. And here it is an energy bar chart. And we're interested in the induced EMF in the loop at each of these following times. And we are given that period is t, and we can figure out how that relates to omega. But we're just going to think about what is happening. So we know for sure that EMF is d flux dt. And this might be a case where you actually might want to do B first before A. I actually think it's easier to derive the expression than think about the energy bar chart, but regardless, we'll go in order. So if I look at flux, with respect to time, and I'll block out quarter cycle, half cycle, 3/4 cycle, cycle, close enough. The flux starts, cosine 0 is 1, and based on this picture, it makes sense because the entire circle is being pure straight now. So I start with maximum flux, and it's a cosine curve, so a quarter cycle later, it would be 0 flux. That's when the loop is on its side. Then a quarter cycle later, depending on direction, we'd flip and be maximized, and it comes back up, and then it returns to where it was originally. So we have this nice sort of cosine curve like this. Of course, if I'm being technical, I probably should like do the absolute value of phi in here, but regardless, this will help us visualize. So EMF is d flux dt. So I have zero flux change at 0, because I'd have a horizontal tangent. I'd have 0 flux at t halves, because I'd have a horizontal tangent, and I would have 0 flux at t. So I know for sure I have 0 flux change at 0 and t halves. Yes, I have maximum flux, but I don't have maximum flux change. But where we see we do have maximum flux change would be at this inflection point. Is this an inflection point? No, it's not. We'd have maximum flux change where we can take the slope right here. So notice that it gave us maximum EMF at 3/4 t, and that's the same thing we see at 1/4 t. So we have the same EMF at 1/4 t. So at a quarter cycle, it's going to maximize its EMF, because again, we're just looking at the slope. I think it's actually way easier to do part B first and then try to fill out the chart from there. All right, derive an expression for the maximum induced current in the loop. So maximum. And the only thing that's allowed is A, R, B, and omega. Well, we're given flux, so it is not a mystery as to what equation we should be starting with. EMF, current, and flux, well, that's Faraday. The induced EMF, in terms of magnitude, is going to be whatever d flux dt is in absolute value. And nothing with negative signs is ever graded with Faraday's law, so don't worry about that. So I'm just going to take the derivative with respect to time of BA cosine of omega t. So that would give me the absolute value of BA times negative sine omega t, because derivative of cosine is negative sine, times omega from the chain rule, so I will not forget that. And then I get BA omega absolute value sine omega t. So that would be the induced EMF, but we're actually interested in the maximum. So we know that sine omega t is trapped between 0 and 1. So when this is maximized, we know that this is max value of 1. So this means that the maximum induced EMF is just going to be BA omega. And then we just need to find the induced current. So the induced current, I max, is just going to be the maximum EMF divided by resistance, just using Ohm's law. So we get, very simply, BA omega divided by R as our induced current. Now we're going to graph the power dissipated by the loop as a function of t. So here's some things we have expressions for. We have expressions for EMF, and we have expressions for current, and we want to relate that to power. So I think the easiest thing to do here is write our power formulas. So on the formula sheet, you're given power is I delta V. But we should also use the fact that we could write this as delta V squared over R, or I squared R. And delta V is just the EMF here. So we're going to use the fact that I am really just graphing the square of the EMF divided by resistance. So let's just think about what this is doing. So going back to our graph, we said that the flux change, or the EMF, starts at 0 because there's no slope, then it maximizes at a quarter cycle, then at 0, then it maximizes again, then it goes back to 0. So again, there's 0 flux change through the loop at 0. There's 0 flux change to the loop at t halves, and there's 0 flux change to the loop at t. So then we see that flux will be maximized every quarter cycle between those. And notice it's always positive because power is a positive quantity. So we just get our remarkably not terrible sine curve between the 2 points. I could try to redraw this, but I'll probably do worse. So this is what our power looks like. Because we know it's going to be maximized at the quarter cycles, and it's going to be minimized at the half cycles. Indicate whether the sketch you drew in part C is consistent with the bars you drew in A. Okay, let's see what the bars are saying in A. The bars in A say I have no EMF at 0 and 1/2, and I have maximum EMF at 1/4 and 3/4. Wow, that's exactly what we have. It's almost like I used that to graph this. So we want to justify our answer referencing functional dependence, and that just means how does power depend on EMF? Well, yes, they're consistent because power is proportional to the square of the induced EMF. So that just means power is maximized where EMF is, maximized. That's a new word. Maximized. So this shows consistency because there's 0 EMF and power at 0, t halves and t, and there's maximum EMF at /power at t equals 1/4 and 3/4 cycle. So you probably did have to say this relationship somewhere, that power depends on EMF squared. All right, now let's grade this one. This was a very fair TBR. First, your 3 diagram points. This appears to be the solution for each of the 3 points. So it's not really a bar adding thing, like we know it's the same magnitude, so you had to draw this exactly to get 3 points. Most likely. Then for our 4-point B derivation, you got a point for a multi-step derivation involving Faraday's law. You got a point for a likely correct derivative of the flux equation. You got a point for correctly figuring out that sine is bounded by 1. So you get rid of the sine, basically. And then you get a point for a consistent substitution into Ohm's law. So I imagine that's how the 4 points are distributed. Then for our 3-point graph, thinking about this, you'd probably get a point for a graph whose period is 1/2 of the original period. You'd get a point for having it maximized at t/4, and you'd probably get an expression for it being minimized at, or no, you'd probably get an expression, yeah, this would be like a sine curve also, and minimized at t equals 0, probably. It's hard to say. I'm not confident that's how they'd be distributed. I imagine drawing some sort of a sine curve as a point, getting it maximized and minimized as a point, in some sort of period relationship as a point. Not sure, though. Then for D, it's your 2 points. You get a point for saying if it's consistent or not, and again, if it wasn't, you just say that, and that's fine. And then you get a point for your justification. And I imagine your justification did have to use the fact that power has this relationship where it's proportional to EMF / the square of EMF. All right, now for our lab question. This one, if anyone who did my practice exam, this was identical, or almost identical to my lab question. So I wrote a question just like this, where you had to design a procedure to calculate resistivity of something. And once again, my setup was more convoluted than this one. So we're basically finding the resistivity of some mystery object that's a cylinder. So first we got to design our procedure. So we're given basically the amp meter and the current and the voltmeter and some sort of a variable battery. So our general setup is going to be measuring the current through and voltage across this resistor type object. Can I line this up properly? Yep, I can. And then use that along with its geometry to calculate its resistivity. So we're going to wire the ammeter in series, voltmeter in parallel. We also need to find the area and length of this object, which we're given a ruler for, because we know that resistance is equal to resistivity times length divided by area. So this means that our experiment to find resistivity must find resistance and whatever L and A are. So eventually we're going to find resistance. We'll use that with Ohm's law. And then L and A are going to be measured / calculated. So this is actually a kind of an involved procedure for A. Usually it's not this many steps, but hopefully it's nothing we haven't seen before. So I'm just saying something along the lines of measure the length and radius of the cylinder, use that to calculate the area, because we're going to need length and area later. Then connect the voltmeter in parallel, ammeter in series, record the voltage and current in the relevant places using the meters, and then to reduce uncertainty, vary this variable power supply, meaning you're collecting various pairs of delta V and I values. Pretty straightforward. So this is basically an Ohm's law lab. So describe how you could collect this data, or sorry, how you could graph it to get row 1. Well, Ohm's law tells me that delta V is equal to IR. So again, letting the equation design your experiment here. So this means that I can graph delta V versus I, because that's going to mean the slope is equal to R. And I'm not done, because I did not want the resistance R. I wanted the resistivity. So if I graph delta V and I, the slope will be R. So what that allows me to do is use R equals rho L over A to solve for rho. Pretty straightforward there. So again, we are just finding the resistance first, and then you combine that with the resistance-resistivity relationship. There's so many other ways of doing this one. Like, you could just graph everything at once. I did this sort of intermediate step of finding R. There's definitely other ways of doing it. Now we have experiment 2, which surprises me that it's basically the same, where you're varying the L of a solid cylindrical resistor, and you're measuring its resistance. So again, we're using the same equation. It's really surprising to me they double dipped on this. Resistance is equal to rho times L over A. So what this allows us to do, if we're given data of rho, L, or sorry, R, L, and A, we could just use the fact that resistance is equal to rho times the quantity L over A. So I know a lot of you aren't necessarily the fan of the way I do it, where I like my slope just being the answer. So I'm actually going to graph R on the vertical axis, and on the horizontal axis, I'm graphing the quantity L over A. I'm sure the more common approach is some variation of just graphing R versus L, and the slope would be rho over A, and then you multiply with your slope. No issue either way. It's really a matter of personal preference. I just think there's something nice about the slope being the answer to your problem. So now we're going to graph it, and by graphing it, I mean I did some mining off camera and graphed it because I hate graphing. So here is what my data would look like graphed. So I had to transform this L divided by A data set here. So be careful with your units. So I get my first point for graphing the quantities I said I would, scaling them, and using correct units. I get my second point for graphing the data reasonably well. And I get the third point for drawing a appropriate best fit line. And this best fit line is like basically perfect. There's not a lot of variation in this data, so it's pretty easy to draw best fit here. Again, if you want to do it in Desmos and copy your Desmos down, that works too. All right. Now we're just going to calculate resistivity. Very easy for me because I picked the easiest graphing relationship type where the slope is just the answer. Oh, there's also RA versus L. I forgot about that one. When we did this as a lab, a couple students like doing RA versus L. So we're given the fact that from Desmos, our savior, or y2 minus y1 over x2 minus x1 enjoyers can do it that way as long as you show that. Desmos, I'm going to check my notes for my regression here. Desmos told me that y was equal to 0.0039 x plus 0.1. So what that means is that for me, my slope was equal to the resistivity I wanted. So therefore, I just look at the slope in my equation to get rho 2 is equal to 0.0039. And then for units, because this one has one that we probably might not remember, it's just my slope. So my slope would be in units of ohm divided by per meter. So ohms divided by 1 divided by meters gives us ohm meters. And this is a reasonable value for resistivity. It varies widely depending on how conductive the material is. So pretty solid lab question. We'll grade this out of 10. So part A is 2 points. I imagine you got a point for some sort of, let's see here. Well, you definitely got a point for varying delta V and doing multiple trials. And then you got a point likely for measuring voltage, voltage and current probably. I don't know if you had to explicitly say how you get the length and area in this part. You should indicate how you use it. So maybe you do have to say that the area or some sort of geometry has to be measured also. So probably measuring voltage, current, and geometry is a point, and then reducing uncertainty via trials is a point. Then, out of 2, once again, you get a point for a valid relationship that is graphed, and then you get a point for a valid analysis. Then for the design, then for the analyze their experiment, you get 1 point for a actual linear relationship. Doesn't matter which one. Doesn't matter order of axes, all that stuff. Then you get 3 points for graphing. So 1 point for scaling, 1 point for plotting, 1 point for best fit lining. Then for D, you get 1 point for relating your answer to the equation, or the slope to the equation that you're using for resistivity. And then you get 1 point for the actual answer. And this could be arranged, but it's probably a pretty tight one if you did regression. If you did it by hand, it's much more open. Pretty straightforward for the lab. I'd say this is my favorite question of the 4, is this magnetism question with wires. I thought this was a really good QQT, even though they didn't put the normal QQT thing here if you can't reference equations. We have 2 spheres that are charged moving near some wires. The wires carry the same current, but the direction is flipped. And we're interested in comparing the magnetic force acting on each sphere. So the best way of doing this is understanding that, of course, this is going to be related to magnetic fields and the QV cross B force. So we're really just comparing B, because Q and V are the same. So wire S, just using the right-hand rule. So again, I stick my thumb in the direction that the current flows, and then I wrap my fingers around. So for wire S, my fingers pop out of the page above wire S, and they go into the page below wire S. So anything above wire S gets an out of the page B field, anything below wire S gets into the page B field. Then for wire T, well, I'm actually I'm only above wire T, so it's going to be into the page, sort of at both locations from wire T. Let's make that bigger. So now, as you can see from my picture, we have sort of different effects happening. So from sphere 2, we're going to have both fields into the page. So sphere 2 has two magnetic fields that are adding to each other. So they're both trying to get a field in the negative k hat direction. But then for wire S, the fields are actually canceling somewhat. They don't cancel totally because wire T is farther away. But we see that we have open circle and X versus X and X. So essentially, that's just telling us that the force on charge 2 is going to be bigger because the fields are additive between the wires and subtractive, to make up a word, outside. So here's my giant paragraph I had to come up with to figure out how to do this without a whole bunch of math. It is really just what I talked through. Force is QVB. Since Q and V are the same, we're really just comparing the net magnetic field at each point. So at the location of the first sphere, wire S generates an out of the page into the page out of the page field. Wire T generates a field into the page. So again, I just explained that. Then I explain what goes on with the second sphere. We know that the magnitude of the field from wire S is the same at each location because it's both D above and below. So the purple field is the same magnitude. And then we just look at what the green field is doing. So since wire T is adding in between, but subtracting outside, there's going to be a stronger magnetic field at sphere 2, so sphere 2 experiences a bigger QVB force. Really interesting little QQT there. I really like that part A. Now part B, we want to find the magnitude of the total magnetic field at sphere 2. So we're just going to use the fact that it does say to start from a physics principle, so it might get a bit dubious as to point assignment later, but I might start with the fact that the net magnetic field is going to be equal to the magnetic field from S plus the magnetic field from T. That might be my fundamental principle. This is called superposition. But what I think they're going to go for your fundamental principle that you have to write somewhere is I think they're going to make you derive the wire formula because that's not on the sheet, even though I'm sure you all have it memorized. So we actually have to use Ampere's law here. The integral of B dot dl is equal to mu naught I enclosed, but it will just be I. So for a wire, we know it circulates around the wire, so we pick a 2 pi r as our Amperian loop. And this gives us that familiar wire formula we've memorized and used a cajillion times. B from a wire is mu naught I over 2 pi r. Part of me thinks you have to derive this, but we'll see. Then we just apply the net magnetic field relationship. So the net magnetic field is just going to be, well, from wire S puts an into the page field. So I have mu naught I over 2 pi d into the page. And then wire T also has a magnetic field into the page with a separation distance of d. So we see that since they're both in the minus k hat direction, they add like we said they should. So we just get mu naught I over pi d because we get a factor of 2. And it is in the minus k hat direction, but we just wanted the magnitude, so mu naught I over pi d. That's all we wanted, right? Yep, magnitude of the magnetic field. We didn't want QVB. We just wanted B. Then, this was a really interesting part. I really thought that part C was interesting on this. So they didn't just go for the consistency, they went for the modification. And they did that with Mac also this year. So later, wire T carries a 3I current in the X direction. So the direction of current flipped in wire T, and you tripled the current. So maybe let's compare to what we had before. So before we had this situation, so in the middle of the wires, we had an into the page field from, I'm going to keep my colors the same, purple. We had an into the page field from this wire and an into the page field from this wire. So we essentially had two X's added together. But then if we flip the direction and triple the current, you are still going to be 1X. But by flipping the direction, we right-hand rule it, and my fingers now pop out of the page. So I'm going to denote this as 3 out of the page open circles. So before, we have 1 plus 1 is 2 in the into the page direction, and now we have -1 plus 1 plus 1 plus 1, which is 2 in the positive direction. So what we have is actually the same field strength, but just reversed in direction. So it's actually equal because we're asking about the magnitude of the force, which is once again QVB. So we're just looking at the QVB force. And since B is the same in magnitude, it's the same force. So here's my explanation. Magnitude of the force stays the same. We could say that B is the magnetic field strength generated by each wire at that location because it was equal distances, equal currents. So it was originally the same B. So from wire S, we still have that same B field, but from wire T, you triple it and flip its direction. So you essentially go from a 2B in one direction to a -2B, meaning the direction flips. So the direction changed, but the net magnetic field magnitude did not, so the force is the same. So pretty interesting choice there. All right, let's grade our 8-point QQT. This is out of 3. 1 point for a correct selection that F2 is greater. Probably 1 point for saying that we are essentially comparing the net magnetic field at each point with QVB relating to force, so saying that we're really just relating the net magnetic fields. And then you get a point for this saying that the fields are additive at sphere 2's location, but destructive at sphere 1. And again, I don't think you're locked out of justification points if you pick the wrong one. Then for a 3-point derivation, I think you get a point for using Ampere's law to come up with this expression. Maybe you get a point for using it, but it says starting from a fundamental physics principle. So I don't think that since this is provided, you can just pull it out of nowhere, even though it's very helpful and it's almost assumed you know this. Then you probably got a point for vectorially adding the two magnetic fields, and you got a point for a correct answer. So if I said that the B fields have to be added and some semblance of vectors going on, that would probably be my second point. So again, I'm thinking you get a point for the wire formula, a point for some sort of net field, and then a point for your answer. Then for the modification, it's out of 2 points, 1 point for the correct selection, and 1 point for justification. There's definitely other ways of thinking about this than I did. I haven't looked at any other solutions yet to this, so this is entirely what I was thinking. So yeah, there's Form J. I thought this was very fair. And I know that my students who had J felt like they absolutely crushed this one. And this is a very fair E&M representation. You got your Gauss, you got your induction, you got your circuit, and you got your magnetism. So this is a very straightforward problem set. There are definitely some tricky parts, but I felt overall, hopefully we found some success with this one.